So let's take a look at how we can use what we just learned from the graph about instantaneous rate of change to talk about how we might do this on a table. Now, tables are really important because most of the time in the sciences, when you're evaluating what's happening with functions, it's based on data that you've collected. So in physics, biology, chemistry, a lot of times there are experiments and you're charting the different values that you have. So you don't actually have a function that models the whole thing, but instead you have various points that you want to use to make some calculations and assumptions about. So we're going to look at some tables and we're going to look at how we can apply what we've just learned to find and approximate instantaneous rates of change. So remember, our goal is to look at the average rate of change near the point to help us make decisions about what we think the instantaneous rate of change is going to be. So consider that I've thrown a tennis ball up into the air and I have the ability to measure the height of the ball, called S of t, in feet for time t in seconds. And I've recorded the data in the table below. So I'm interested in trying to approximate how fast the ball is traveling when time equals 1 second. So the way I read the table before I've done any analysis on it is that time equals 0, the ball is 6 feet in the air. So if you imagine a person standing up and they're throwing a ball up in the air, when they let go, their hand is probably about 6 feet off the ground. So that makes sense. After 1 second, the ball has reached 9 feet in the air. After 2 seconds, it's 11 feet in the air. After 3 seconds, it's 12 feet in the air. But then at 4 seconds, it's 10 feet in the air. So it started coming back down. So that's what's happening if you're trying to visualize. But I want to know, how fast is that ball moving at time equals 1? Now, because I don't have the actual function that models this situation and I just have some points, that means that I'm going to be doing an approximation. So I'm going to get my best guess mathematically at how fast that ball is moving, while keeping in mind that if I had the actual function, I'd be able to get better information. So again, our goal is to look at the average rate of change near the point I'm interested in. So I'm interested in what's happening at time equals 1. So what I'm going to do is I'm going to calculate the average rate of change to the left of my point and the average rate of change to the right of my point, just like I did on the graph. And I'm going to use the closest point that I have because that's the most accurate data for what I'm looking at. So let's start by finding the average rate of change to the left of 1. So when I say to the left, that means I'm going to be using the information at 1 and the point directly to the left of it. So again, I'm going to apply this to my average rate of change formula. So I'm going to do f of 1 minus f of 0 over 1 minus 0. So f of 1 means I'm going to go to my table and find the dependent value. So I have 9 minus, now f of 0 is going to be 6 divided by 1. So this is going to be 3. So remember that sometimes we can attach units if we're given them in the problem. So this 9 and this 6 on the top, these are both dependent values. So that's in feet. And then on the bottom, the 1 minus 0, the units on that is seconds. So this is 3 feet per second. So my average rate of change between 0 and 1, which is to the left of 1, is 3 feet per second. I'm also interested in looking at the average rate of change to the right of 1, just like we did on our graph, because we want to look at smaller and smaller intervals around 1 on both sides. So to the right, I'm going to be looking between 1 and 2. So I'm going to do f of 2 minus f of 1 divided by 2 minus 1. So that's going to be 11 minus 9 divided by 1. And that's going to give me 2 feet per second. So my average rate of change to the right is 2 feet per second. Now, because I have a table, I can't make this information any better. I don't have a way to get closer and closer like I did with the graph, because with the graph, I had the function and I could just keep plugging things in. But here, unfortunately, I don't have a good way to do that. So my left hand approximation was 3 feet per second. My right hand approximation is 2 feet per second. Since I can't make that any better, my best guess is going to be to average these two numbers together. So that means I'm going to add 3 plus 2 and then divide by 2. So my best guess for the instantaneous rate of change is 2.5 feet per second. So again, this is an approximation. This isn't an exact. So when I write about this and I talk about the instantaneous rate of change, I'm going to be using the approximation symbol. But it is a fairly good guess because I know I have to be between 3 and 2, and there's not too much variability between there. Now, a note about the units. So again, we get the units of the average rate of change because we're taking the dependent units, which were on the top of our formula, divided by our independent units, which were on the bottom of the formula. Since we're using the average rate of change to approximate the instantaneous rate of change, the units of the instantaneous rate of change are also going to be in feet per second. So again, you can take the average rate of change units, and those are going to be the same as the instantaneous rate of change units because we're using the average rate of change to get to the instantaneous rate of change. Now again, not every problem is going to have units, but when they do, you should go ahead and start using them because they're going to become more and more prevalent as we go. Now, just like on the graph, if we were able to get closer to 1, our approximation would be a bit better because our bounds wouldn't be so far apart. So let's take this example and let's extend it a little bit to see how this might work on a table. So now let's consider that during our experiment, someone with better tools than I have was also measuring the height of my ball. In fact, they were able to measure every half a second. So now my table has more data. Notice that at 0, 1, 2, 3, and 4, that those positions are the same. The position didn't change. What happened here is that I now have more information about where my ball was at 0.5, 1.5, 2.5, and 3.5. So the numbers you see in red are additional information than what I had before. However, what I had before didn't change. So now, when we want to try to figure out how quickly my ball was moving at time equals 1, I have closer information. So let's see what kind of impact that has on my calculation. So again, we're going to look at what happens when we take the average rate of change to the left and the average rate of change to the right. So what's going to happen here when I take my average rate of change to the left is that I'm now going to use the 1 and the 0.5 because the 0.5 is the closest point on the left of 1. So I'm going to do f of 1 minus f of 0.5 divided by 1 minus 0.5. So again, on the top, that means I'm going to do 9 minus 7.8 divided by, now on the bottom, 1 minus 0.5 is 0.5. So 9 minus 7.8 is 1.2 divided by 0.5 is going to give me 2.4 feet per second. So again, the units are going to be feet per second for the same reasons that we had above, because the dependent variable is in feet and time, which is in the bottom, is in seconds. Similarly, we're going to calculate the average rate of change to the right of 1 using the closest point to the right, which is now the 1.5. So we're going to have f of 1.5 minus f of 1 divided by 1.5 minus 1. So that's going to give me 10.1 minus 9 divided by 0.5. So that's going to give me 1.1 divided by 0.5. And when I put that in my calculator, I'm going to get 2.2 feet per second. So here we can see that by getting closer to 1, our approximation has become much, much better. So now we know that the instantaneous rate of change, or the speed at which my ball is going up into the air, has to be between 2.2 feet per second and 2.4 feet per second. That's pretty close. Again, my best guess would be to average these two numbers together, which would give me 2.3 feet per second. So without any further information, I would make an approximation of 2.3 feet per second. And again, that's only if I can't make it any better. But let's see what happens if I can make it just a little bit better. So finally, let's consider that during our experiment, someone who has the best measuring tools was also measuring the height of my ball, and they were able to measure every 1/100th of a second. So almost at every single moment in time. So again, I could fill in the data for every 1/100th of a second, but that would make the table really, really big. So instead, I'm zooming in on what the data points around 1 would look like if I had measured every 1/100th of a second. So here, again, I want to do an average rate of change to the left of 1 and an average rate of change to the right of 1. And if we're going every 1/100th of a second, that's going to be really, really close. So when I do the average rate of change to the left, I'm going to do f of 1 minus f of 0.99 divided by 1 minus 0.99. Now when I put this into my calculator, there's a lot of decimals. So I saved all the decimals and crunched them all at once. And when I put it all in, I got 2.3645. So that was the exact number I got. I didn't round that. Now, when I do the average rate of change to the right, I'm going to be doing f of 1.01 minus f of 1 divided by 1.01 minus 1. And again, I took these decimals and I crunched them in my calculator very, very carefully. And I got 2.3645. So what's happened here is we got so close to 1 that we got close enough that we don't even have to make a best guess anymore, because the average rate of change on the left became the same as the average rate of change on the right, which means that that is the exact instantaneous rate of change. So my instantaneous rate of change here is 2.3645 feet per second. So again, if the average rate of change on the left is the same as the average rate of change on the right, you've gotten to the point where the lines are the same and you have that tangent line. And the slope of that tangent line is 2.6345. So at time equals 1, at the 1 second mark, that's how quickly my ball was moving in space. And again, that's telling us the change of the function at that point. And change always tells us how much the dependent variable changes for every 1 unit that you move in the independent direction. So that means that at this particular moment, that if I were to move 1 second into the future, that my ball would go up 2.3645 feet. So 1 unit in the independent direction, which was time, would result in a 2.3645 increase in the dependent direction, which is the height of the ball. So I was able to get the exact instantaneous rate of change. Now, let's summarize the important points here about instantaneous rate of change. The instantaneous rate of change is how much a function is changing at 1 point. And the way we get the instantaneous rate of change is by looking at average rates of change around the point we're interested in, and we want to get as close as possible. Sometimes we can't get that close, and if that happens, we have to use our best guess by averaging the average rate of change on the left and the average rate of change on the right. However, if we are able to get closer, we're able to shrink the interval and make a better guess about what our instantaneous rate of change will be. The instantaneous rate of change is the slope of the tangent line, if we are able to find it, for a function at a given point.